Welcome to Summarize Science, where we break down the latest breakthroughs in physics for everyone to understand. Today, we are looking at a study that tests the fundamental idea in our universe, the Weak Cosmic Censorship Conjecture. Proposed by Roger Penrose, this idea suggests that the singularities inside black holes, where the laws of physics break down, are always hidden from us. They are tucked away behind an event horizon, which is like a one-way door that light can never escape from. If a singularity were naked or visible to an observer, it would mean the universe becomes unpredictable, which is a scary thought for scientists. To test this, researchers use something called phantom fields, which are a bit like the opposite of normal matter. While normal gravity pulls things together, phantom fields have negative energy and create a repulsive force. The goal was to see if these strange fields could collapse into a singularity without creating an event horizon to hide it. The study used highly accurate numerical simulations to follow how these wave packets evolve over time. Usually, when a lot of energy is packed into a small space, a black hole is the expected result. The researchers set up their digital experiment using two different shapes for their energy waves, a Gaussian pulse and a tan-like step. By varying the strength and width of these waves, they looked for any sign that the math was about to create a naked singularity. They used a specialized coordinate system to keep the math as simple as possible while the simulation ran. To ensure the results were accurate, they included a dissipation term to smooth out any tiny numerical errors. This allowed them to focus on the real physical behavior of the phantom fields under extreme pressure. In a standard scenario with positive energy, a massive wave eventually collapses into a black hole with a clear event horizon. But with the phantom field, the effective energy density can be negative, which changes the outcome entirely. The study monitored a value called the Crutchman scalar, which measures how much the local spacetime is curving. If this value were to blow up to infinity in a way we could see, it would signal the birth of a naked singularity. Initial runs of the simulation showed the math breaking down at very high energy levels, which was a suspicious sign. At first, it looked like the simulations were hitting a physical wall, suggesting something new was happening. However, the researchers investigated further to see if this was a true physical limit or just a computer error. They found that as the energy increased, the speed of the signals in the simulation grew significantly. This triggered a problem with the time step of the simulation, known as the Courant stability condition. By adjusting the simulation to run with much smaller time steps, they were able to continue the calculations without any crashes. The final results showed that even with massive amounts of negative energy, a naked singularity never actually formed. Instead of collapsing into a permanent hole or a naked point, the phantom field simply bounced and dispersed away into space. This means that even in a setup designed to break the rules, the universe seems to protect itself. The repulsive nature of the negative energy was strong enough to prevent the singularity from ever completing its formation. The curvature of space reached a peak but eventually smoothed back out as the waves moved outward. To recap, this research demonstrates that the weak cosmic censorship conjecture is incredibly robust. Even when the researchers intentionally used illegal types of matter that violate standard energy conditions, the universe didn't break. No black holes with negative mass were formed, and no naked singularities were exposed to the outside world. For the future, this suggests that our current understanding of gravity is very stable and predictable. It gives scientists more confidence that even the most extreme corners of space follow the rules of causality. Thanks for watching Summarize Science, and we will see you in the next breakdown of the universe's mysteries.